Hello everyone, welcome to Prakriya Educations. I am Mallikarjuna. In this module, we shall solve a few problems on types of functions. Check out the next problem. Prove that the greatest integer function, which is defined as f from r to r given by f of x is equal to the square brackets of x, which denotes the greatest integer less than or equal to x, is neither 1 nor onto. Before entering into the problem, be clarified with the greatest integer function. If I am writing some number within this brackets, for example, if I am writing 1.2, then the value of 1.2 will be the integer which is less than 1.2. In the real axis, you may now note, if you are marking the point 1.2, it will be somewhere here. This is 1.2. If the value within the brackets 1.2, the value of this will be equal to 1. The integer which is less than the given number. Now, if I am writing 1.9, which is the integer which is less than 1.9, don't confuse with the round off concept. 1.9 with the greatest integer function is nothing but the integer which is less than 1.9. Therefore, the value of this will also be equal to 1. And therefore, you may note that the values of 1.1, 1.2 until 1.999, the values of all these functions will be equal to 1 itself. Now, if I am writing 0.5, the greatest integer function 0.5, the value of this will be 0. The greatest integer function 3.9, the value will be 3. This is the concept of greatest integer function. Now we shall solve the actual problem. We need to now prove that the greatest integer function is neither 1 nor onto. Let us have a random arrow diagram. If I am taking the real number sets, I cannot absolutely write the real number set. In precise, I'll just write the numbers which I need. Yes, now the function f is defined from r to r as f of x is equal to the greatest integer function x. As per the definition again, yes, 0 will be mapped to 0, 1 will be mapped to 1, 2 will be mapped to 2. How about the decimals? 1.1 will be again mapped to 1, 1.2 to 1, 1.3 to again 1, 1.9 also to 1. In the given arrow diagram, you can clearly note that many elements of the domain R is mapped to the same element of the codomain R, and hence you can conclude this is not a 1-1 function. And also observe that there are many elements in the codomain R which is not being mapped with any element from the domain R, and hence you can also conclude that the given function is not an onto function. Now, writing in a general way, you can give a counter example even for this. Starting with 1-1 function, you can note here f of 1 is equal to the greatest integer function 1, which gives us 1 itself. F of 1.1 gives us 1.1, which will be again 1. Then f of 1.2, which gives us again 1, and it goes on. Hence, you can now clearly tell that f of 1 is equal to f of 1.1 is equal to f of 1.2 is equal to so on until f of 1.99 will also be equal to the same number 1, and hence write as different elements of the domain R has same image, right? And hence you can conclude that f is not a 1-1 function, right? Now going on for the second one, that is for proving whether it is onto or not. Again, look at the arrow diagram. You can give a counter example. I'm choosing some random element. Okay, I'll choose 1.3. 1.3 belongs to the real numbers R, which is in the codomain, but there does not exist any element X in the domain R such that f of x is equal to 1.3, right? That is, I'm just writing it as there is an element 1.3 in the codomain, but 1.3 is not being mapped from any element in the domain, and hence you can conclude that f is neither onto, right? And hence conclude even that f is not a bijective function. Hence we have proved that the function, that is greatest integer function, is neither 1 nor onto. Check the next problem. Show that the modulus function f from R to R given by f of x is equal to mod x is neither 1 nor onto. Now recall the definition of modulus function, that is f of x is equal to mod x is given as plus x for every x greater than or equal to 0 and minus x for every x less than 0. This is the formal definition. Coming to the practical examples, if you are having a positive number inside the modulus function, you will retain the value as it is. If you are having any negative number inside the modulus, you will again retain the positive value itself. This is the concept of the modulus function. If I am drawing the arrow diagram for the given function, the function f is defined as f of x is equal to modulus function of x. Now going on relating the elements, you can check that modulus of minus 3 gives us plus 3. Modulus of plus 3 also is plus 3. Mod of minus 2 gives us plus 2. Mod plus 2 also gives us plus 2. Similarly for modulus of minus 1 and mod 0 gives us 0. You may clearly note that plus 3 minus 3 is been mapped to the same element 3, and hence you can conclude that it is not 1 and you may also notice that all the negative numbers which are there in the codomain R is not being mapped, and hence you can conclude that the range of the function is not equal to the codomain, and hence it is even not an onto function. Writing it generally using the counter examples for the 1 function, you can tell that f of plus 3 is equal to modulus of plus 3, which gives us plus 3 back. F of minus 3, which is mod of minus 3, which again gives us plus 3. Therefore, f of plus 3 is equal to f of minus 3, has the same image plus 3. Therefore, different elements of the domain R has same image, and therefore conclude that f is not 1 function. Right? Now we shall solve for the second one, that is for the onto function. Again you can take any number which is not being mapped. Okay, if I'm taking minus 2, minus 2 belongs to the real number set, that is in the codomain, but there does not exist any element x which belongs to the set of real numbers, that is in the domain, such that f of x is equal to minus 2, and hence you can conclude that f is not onto function, and therefore obviously f is not a bijective function. Therefore, we have proved that the modulus function is neither 1 function nor onto function. Check out for the next problem. Show that the signum function f from R to R given by this function is neither 1 nor onto. Remember that if I am taking the signum functions from the set R to the set R, I shall take few numbers which I need again. Now the function f is been defined from the set of real numbers to the set of real numbers as the Signum function. As per the definition of Signum function, for every x which is greater than 0, that is for all positive numbers, all the positive numbers will be having the value as +1. All the negative numbers will be having the value as -1, and x is equal to 0 will be having the value as 0 itself. Now trying to map that, as per the definition, +1 will be having which is greater than 0 and hence have the value as +1, +2 greater than 0 again as +1, +3, +4 if you are having, even that will be mapped to +1. All the positive numbers will be mapped to only a single element +1. 0 will be mapped to 0 itself. All the negative numbers will be mapped to -1. Observing it, you can easily notice that many elements of the domain is been mapped to a single image, and many elements which are there in the codomain is not being mapped, and hence the function given, that a Signum function, is neither on1 nor on2. Now writing this generally, you can use the counter examples. Now, for the 1 function, you may select that f of +1 is equal to f of +2 is equal to f of +3, so on, will be having the value +1 itself. F of -1 which is equal to f of -2, f of -3, so on, will have the same value -1. Therefore, different elements of the domain R has same image. Therefore, you can conclude that the function f is not a 1 function. Fine. Now secondly, proving for the onto, again you can give a counter example. Choose some random value in the codomain R which is not being mapped. Okay, if I am choosing -2, -2 belongs to the real number set, that is the codomain, but there does not exist any x which belongs to the domain R such that f of x is equal to -2, and therefore f is not onto function, and obviously you can conclude f is not a bijective function. And therefore we have now proved that even the Signum function is neither 1 nor onto. Hope you enjoyed the video. Please don't forget to like, share and subscribe. Thank you.